Alright, so, first, when it rains, guys, the farmer's market doesn't actually happen. Okay? So unfortunately today it's not going to happen, I can tell you right now. It's fine, we'll start next Thursday, and we'll do the Thursday after that also. Same thing, we're going to do 2 weeks.
So, you want to go,
I know.
in 2 days, you're trying to get like 2 million pounds of corn.
What we need, really, we need about 500 pounds of cornstarch. What does cornstarch actually cost for one of those containers at the store? Like $1 and change?
And I know it's yellow,
We're talking like $500 worth of cornstarch. Even if we don't get it, you can get like 200 at least, so you can make something out of it, you know what I mean? The farmer's market? Oh, absolutely. They do a lot of stuff over there.
Yeah, it is. Once you cross the
I'm sorry to be so blunt, but I'm just saying, just the.
People will break stuff like that. And to be honest, Houston, I live over there, I've been there a lot, and that farmer's market, that's why I'm doing it there, because I know the guy well, he doesn't mind doing community events. But I can't just go to like a random farmer's market and just.
Good side.
He lives on the good side, where the police actually goes through
There's
there.
no bad side of Riverdale.
Sure, whatever close to building. Okay.
Once you cross that good over behind, you're through there. On the way. Hey, son, once you cross good over past, that's the problem.
So he just don't want to.
So anyway, people that are not here, people that are not here, that we're gonna help today, I think we're just starved, I think it's just starved, that's not here that was gonna help. So somebody should get that message across to her at some point today. She's at the Celebrity Waiters Luncheon, right?
Yeah.
Okay, so somebody after school maybe text her real quick and say, hey, farmer's market isn't on because of the weather, but we're postponing to next Thursday. Let her know, please. If she doesn't show up, be courteous, she's helping out the school today. Alright, so here's what we're going to do today.
We just talked about this.
We're going to start by looking at that last example I ended class with, that I told you to do for homework, so take that out, please. Take out your example for lead, please.
I think I actually figured out the problem. I forgot it.
You think you actually figured it out and forgot?
I figured it out before we left. I had to answer my head, I wrote it down.
So how much mass do we have for the lead? What was the mass of it?
20 kilograms.
10 kilograms? Okay, Maria, what was the other information that we were given? Change in temperature and stuff?
Yeah. It charged from 2,000 Celsius to 2,500 Celsius.
Okay, and I gave you the specific heat of lead.
Yeah, it's 1.28 times 10 to the second power.
Thank you. Anybody know the symbol for lead on the periodic table?
Yes.
Wait, I have to figure out MN.
K.
Without looking, come on.
L.
Without looking.
G.
I thought it was like H.
No, that's Mercury.
Hg is mercury.
MN.
This is Greek or something.
L. M. N.
Z.
O. P. Q.
I-N.
Pb.
I said PB. Come on.
I heard 20 other things, I just didn't hear you. That's why raising hand works pretty well, alright? So, I heard AU, which is gold, I heard HG, which is mercury, AS, I think is silver, or no, AG is silver. There's a lot of them. Anyway, so the specific heat of lead. If you want to write lead down, write lead. Okay? Pretty sure it's PV, somebody can verify that, but I'm almost positive. I bet on it, but it is. Alright, I also told you that the boiling point of lead, where was I? The boiling point of lead was
1,744.
Very good.
Still covered.
Alright, so the first thing we have to recognize, there are two things in this problem. We're asked to find the heat change or the heat exchange that causes this lead to get heated up. Now, the first thing we have to think is this. What phase are we starting in?
Liquid.
What is it? Gas. Because the boiling point is 1745. If the starting temperature is 2000, it's above the boiling point. Thus, the lead has boiled off. So we're in gas form now. Are we clear on that? It's very important that we know that. Again, we're starting is a gas. And then we're increasing to 2500, which is still going to be a gas. So are we doing any phase change here?
No.
We are not. We didn't learn how to do that yet. That's what today's lesson is about. Okay, we're going to learn how to do phase changes. So if you're not changing phases, you can simply use Q equals MC delta T.
Not changing.
Okay, when you're not changing phases. About
When you're talking about the equation, you're trying to figure out, what were we just trying to figure out what was the
we're trying to figure out if we're changing phases here.
The boiling point, I'm sorry.
But we're given the boiling point. Since we know that we're above the boiling point, it must be a gas. It's still above the boiling point at the end, so it's still a gas. So we're not undergoing any phase change. There's going to be no molecular bonds being broken.
I'll find that in general. Do they have the same boiling point or is that?
No, all things are different. So like lead was 1745, aluminum is 2467, nitrogen is negative 195. I mean, they're all just different stuff. Okay? Depends on what you're talking about. All right.
Thank you.
No problem. So we plug in. I'm going to put 128 here. What's my delta T, everybody?
You're changing.
500 what?
500 degrees Celsius.
Which is the same as?
500 Kelvin.
Good. Remember, it's the same as 5. I knew.
5K, 500K.
A while.
Let's throw that out there.
Yeah.
Okay. Remember, guys, go back to your temperature scales. Celsius and Kelvin are really the same thing, except there's like a horizontal shift
Oh,
of
no.
one of them. Remember when we looked at those temperature scales, Celsius and Kelvin have the same increment size. Let me bring that up again, just to make sure we're all clear on this.
640 times 6
1, 2, 3, 4, 5,
640 times 0 to
10, 11, 12, 13, 14. You
64.
have to open up the mirror tab. The mirror!
Just multiply the 5 and then add the 3 zeros.
Where is that figure? Here it is. Okay? Again. Please, everybody, make sure you are understanding this. Kelvin and Celsius have the same delta, the same increment for each degree. So when Celsius goes up 1, Kelvin goes up 1. It's just that, watch what happens. The Kelvin scale is just shifted over. It's a horizontal shift. That's all that's going on here. So whenever there's something like 0, it's at 273. When it's at negative 10, it's at 263. When it's at negative 20, it's at 253. That's why we add 273.
That's what I was looking at. That's what Kelvin is 9 degree. There's no, in Kelvin, there's no such thing as negative degree.
But Rankine is the same thing, and it has a degree. So why is there not a degree on Kelvin? Answer's still not valid.
Huh?
Rankine is the same as Kelvin for the Fahrenheit
Hey, look,
scale.
that's what they said.
Well, you gotta find a better answer. That's not acceptable.
That's not acceptable.
No, because this is proving you wrong right here. You're telling me that because it's an absolute scale, they drop the degrees. This is an absolute scale. There's degrees on it. Why does the other one not have degrees?
Whoa, we're the absolute.
Rankine goes down to 0. 0 Rankine is absolute 0. It's negative 468, or whatever that number is, degrees Fahrenheit. Or negative 460.8.
I didn't go to Wikipedia. I went to the somebody.edu.
Yeah. It's not the answer, unfortunately. All right. It always takes a screenshot, guys.
Oh,
Hey, we could call the Soviet Union and ask their saying.
So,
Write it. I want to hear.
for this problem, you can convert your degrees to kelvins right away. Then you can subtract them, and you're going to get 500 kelvins. Or you can just subtract your Celsius and realize that 500 kelvins as a delta 500 kelvins as a delta is the same as 500 Celsius as a delta. What does delta mean again?
Change.
Change. That's why this works this way. If you were looking at just a temperature, if you had to do a formula that just asked for temperature, and you need to use a certain value, you gotta use kelvins. But because we're looking at the delta temperature, if we do it in Celsius, it's the same as kelvins. Because that increment value is the same. Yes, sir.
Alright, so I found out that you could actually, change, like, hand sanitizer just all thick.
Alcohol, yeah?
And when you put salt in it, like, it kind of makes it more liquid. Like, it breaks down, like, all that stuff that would normally kill you if you drank it. And, you know, people are not drinking that, it's 120 proof.
Yeah,
Yeah,
well,
I noticed doing that for portrait.
you're talking, yeah, it's like.
No way.
To get a.
Yeah, like, they get so drunk that it's so,
Yeah.
they mess them up.
That's disgusting.
Whoa.
Don't do that stuff, guys.
Sanitizer, 'cause, like, alcohol.
That is
So,
awesome.
That's terrible.
That's retarded.
You know what happened with Advil for a long time, right?
Yeah.
Not with Advil?
Oh,
You know the red Advil?
Would you need
The which happened?
The one that was blue and red.
Oh my gosh.
See, 4 times I looked. Advil cold and sinus, guys. The red box. It's no longer available on the counter. You have to siphon it now. Because for a long time, people realized that if you burn it off at a certain level, you can actually separate the drugs. And they were using one of the separations to make meth for a real long time, which is one of the worst drugs out there. Same idea, I guess, is what they're doing with this. That's really disgusting. You know what that's gonna do though in society? Hand sanitizer is not gonna be available
They
at
use foam now.
at a local store.
Phone or.
Yeah, the foam sanitizer. Or just don't use sanitizer, guys. You don't need it. I've told you this many times. You don't need it. Wash your hands like a human being. Go to the bathroom, get soap. Don't use that stuff. Why do you need hand sanitizer when you're in a car? Honestly.
No, but sometimes
No,
like
seriously, tell me.
sticky stuff or just like.
Okay, so you're gonna have
In
you're
general,
like,
like, or what if you touch like.
you guys are all hooked on this stuff. And I know Miss B uses it, and she'll tell you the same thing that you guys said. Oh, she uses it all the time.
I don't
Don't
use
use it.
Instagram,
If you want me
don't use
to,
it.
I'll put papers on it live tonight or on Facebook that reference all this stuff.
I don't
You
use
don't want to use it. It's killing off all your bacteria, and what's leaving behind is the stronger bacteria. That's why hospitals are so unsafe. Do you know that?
Yeah.
Hospitals have the deadliest strain of viruses because they're so sanitary that the only thing that can exist is the really strong stuff. The hospitals, they are so sanitary that the weak stuff gets killed instantly. So all the strong stuff remains and it multiplies. And that's why in a hospital, there's a strain of bacteria that only exists in hospitals that is really, really, really bad. And a lot of people get sick from it from being in the hospital.
So she was really,
Right? That's right. Guys, last resort, sure. Last resort, sure, but try to avoid it. Try to avoid it. If you go to the bathroom, you better not be using hand sanitizer. Wash your hands. Okay, wash your hands. You do not need to, and not to mention urine is sterile. Everybody know that? Urine is sterile. Technically, I'm not gonna go into detail. But if you end up getting urine on your hand, you can just run it under water, and it comes right off. You don't even need soap. It is sterile, okay? So, whenever you have a chance, use regular soap. Don't use hand sanitizer, please.
I want such a amateur urine.
What about wet wipes? What about it? What do you mean?
Do they work?
I mean, what application are you using them for? Like cleaning a surface of a table?
But they sell like wipes for your hands.
Yeah, that's fine. I mean, most of the time you use that stuff is like, if you go like, imagine you went to Buffalo Wild Wings and you had wings. Your hands are covered, right? That's where you get wet wipes. Right? Don't you get the wet wipes afterward? That's why, because a lot of that stuff doesn't come off with soap. That's why they give you the wipes. But just use soap, guys. Just use soap. Much healthier. Okay? Anybody get a number here?
640,000.
Well, no, I said, where do you look at urine?
Okay? Joules. 640,000 joules is the amount of heat needed. That's a lot of heat. That's a lot of heat.
So how much heat does
Somebody pick up on that? That's saying that's a lot of meat.
oh my gosh, sorry.
It's saying that's a lot of meat. Wow. That's why.
She was cooking, she was cooking.
Exactly.
She was cooking.
Meatloaf.
She was cooking meatloaf.
Get your brain out of the drain.
How much heat
Yes.
is the core, the center of the earth?
How much heat? It's radiation now. The heat, the core radiates heat out from it actually. So that's where most of our heating source
Is
comes
it-
from. It doesn't come from like conduction or
So it's
convection, it
not
comes
as
from the
strong
core.
as the sun's heat, obviously, right?
I don't know. It's a good question. I'll look it up and try and get back to you, but I don't know the answer to that. Whether the core emanates more heat at a higher rate, or the sun gives more heat at a higher rate. I'm not sure. That's a good question. Teresa?
What about how much heat does like straight irons and hot coals use?
A lot of your heat units are usually in BTUs, British thermal units. So you'll say like you have a hot water heater that warms up your water in your house. And they use BTUs because we're in America. They don't use joules because of that. So I don't know the number. I'm not sure. But there's a conversion between BTUs and joules. You can look it up. You can actually go on your apps and your calculator. I think there's a joule. I think there's an energy conversion on there, and you can convert from joules to BTUs and see what they're like. Christian.
So we use fridge.
Thermal units. Well, because that's where we got all of our stuff. Even inches and feet are English. We use the British system because we were colonized by them.
Idiots.
All right, now let's get into today's lesson. So that was a review of the homework. Let's take a look at today's lesson now.
No, I'm not kidding.
All right. So this is not easy what we're about to do. I'm telling you now. The math is very easy. The concept seems to trick people up. So the conceptual part we have to make sure we're down on. Okay, we understand this before we actually go into the math. So if I was taking something like, let's do an example. I'm not going to do water because water is the one we always use, just to mix it up a little bit.
Yeah.
Let's say we were looking at aluminum.
You used aluminum last time.
Did I use aluminum?
Just use it.
Oh, you
man.
use it again.
Yeah, just use it.
Let's use nitrogen, whatever. It's fine. I got a bunch of them here. Okay? Now,
Challenge your
say-
mind.
let's challenge those minds. I agree. Let's say we're changing nitrogen. The initial temperature of the nitrogen is negative 200 degrees Celsius.
Freezing.
Okay? I'll explain in a minute what it is. Whether it's actually freezing or not, we'll figure out. Let's say that we want to get to a
What's
temperature.
the freezing temperature?
That's what I'm going to tell you in a minute. Let's say we want to get to a temperature of negative 180. Okay? What's my delta?
20.
Good. 20. Now, positive or negative 20?
Positive.
Good. Because you're going from a negative 200 to a negative 180, which means you're moving right on the number line, or you're moving up. You're an increasing function. Okay? So, we've got TI and TF now. I'm going to give you two things. First,
And?
the melting point.
I heard a rumor that if in a day your glass, you don't have to take a bite.
And the boiling. And the boiling point.
Ah, that's about right now.
We'll talk about that later, okay? If the melting point of nitrogen is given as negative 210
Wow, never mind.
Celsius, and the boiling point is given as negative 196, I'm approximating by the way, Celsius. I want somebody raise their hand and tell me what's going on with this, what's going on with this problem.
So,
It's not easy.
it's going from a. It's not going from a liquid to a gas. Yeah.
Why? What does it cross along the way? The melting point or the boiling point? Look at your numbers.
It crosses the melting point, so it goes from a solid to a liquid.
Doesn't cross it, dude. No.
No.
What's in between?
What's between these two numbers, guys? Which of these two is?
196.
So automatically, you know that it's going to be either boiling or it's going to be condensing, one or the other, from gas to liquid or from liquid to gas. Since I'm going from a lower temperature to a higher temperature, what's happening here is we're going from the liquid phase
You're adding heat.
to the gas phase by the addition of Q. Very good. By adding heat to the problem. Julian?
What I was saying is nitrogen is a gas. How is it a liquid? Or you just using it for example?
If you cool it down enough, it becomes a liquid. Nitrogen at STP, standard temperature and pressure, which is what we're in, is a gas.
Yeah.
But if you cool nitrogen down enough, you get liquid nitrogen. If you cool it down even further, to negative 200 or negative 210, you would actually get a solid nitrogen, which is very insane to think about.
Put that on your hands.
Which dry ice?
Solid.
Which dry ice?
CO2. It's solid CO2, carbon dioxide. Okay? It's not one element, so I can't just say anything else. All right, so here's the method that we want to be using is the following. Ready? You find your starting, you find your ending, and you see which one of these it goes through. Everybody clear on that?
Yeah.
Again, you find your starting and your ending, see which it goes through. If it goes through the melting point, then it's going from either solid to a liquid or liquid back to a solid, one or the other. If it goes through the boiling point, it's going from a liquid to a gas or from a gas back to a liquid, one or the other.
It went blue.
What's between negative 200 and negative 180?
Never mind. I'll think the other way around.
Okay, all right. So here's the problem with this problem. We have to account for the phase change when we think about how much energy is used. So from negative 200 to negative 196, how many degrees go by?
4.
And that's only changing the temperature, right? Then it hits 196, and what starts to happen? It phase changes for a while. Then it phase changes all to a gas at 196, and then it continues to get hotter until it gets to negative 180. So here's what's going on. I'm going to draw a little picture of it, okay? We've got, it starts at negative 200 as a liquid. Then it starts to heat up by the addition of heat until it gets to negative 196. Okay, with an addition of Q, with an additional heat added on, it goes until it gets to here. Then we have a phase change, and we're going to call this vaporization, remember?
Yeah.
As opposed to
Evaporation.
fusion. It's the same as evaporation, as opposed to means the other.
Oh.
So since we're changing from a liquid to a gas, it's evaporating. We call that vaporization. Then it all evaporates into a gas, still at 196 negative. Then it continues to go until it gets to negative 180 with more heat. And in this phase, it's what again? Gas. So this problem is how many parts? 3. Well done. Here, formula I'm going to use. What have we done already when you change the temperature? What's the formula that we've been using the whole time?
MC.
Not tau, but T. Over here, I'm going to put Q2.
So then what? You add both Q's?
So it takes heat to warm up the liquid nitrogen until it gets to the phase change. It'll change the phase, we'll talk about that in a minute. And then, after that, it takes more heat to get even hotter. The question becomes, how much energy is needed here? And that's what we're going to talk about today. Here's your formula. Whenever you phase change, whenever, it's Q equals ML. That's it.
What the hell is that?
L is given, and we'll talk about that. The latent heat. Remember that latent stuff? Because the latent bonds we talked about? Yes, all of them are given in tables. L is given, C is given, C is given, mass has to be given in the problem, and delta T you can see. L is always given, it's a data value, it's empirical, it's based on the substance.
So in other words, you have to do like 4 out of 5.
Yeah, you're going to need to know, if you want to know all the Q for the whole thing, you need to know the change in temperatures, which are given, you need to know your C values, which can be different based on the phase, by the way. The C value for nitrogen as a gas is one thing. The C value for nitrogen in a liquid could be different.
So that.
Okay? These could be different C values here. The L value has to do with changing the phase. Before I do the solution to this, I want to show you something. Okay? I'm going to show you a table. So take a look at this table now. What the table shows you,
You have too many folders.
what the table shows you here,
I know, right?
I will hope you won't have to sleep.
these are all the tables in your book, and I just put them on a piece of paper here. So these are all right out of your textbook. So when you look at this section in the textbook, you'll see that it's there. By the way, it's chapter 9. So, and you've already read from this section once.
Yeah.
So this is your first table with all of your C values. See all the C values?
Yeah.
Now, be careful here. Take a look. When H2O is a solid, look at the C value. But then when H2O is a liquid, that's the C value. But then when H2O is a gas, that's the C value. So that's what I was talking about. The C value for water is 3 different values depending on what phase you're in, actually. You see that? If it's ice, there it is. If it's gas or steam, that's the C value. If it's liquid, that's the C value. But for something that we just did, like nitrogen, of course, I don't have it on here. Awesome. Okay, we'll figure it out. Now, the next thing, that's the first table. Here's your second table. You're given some values here, and you're given these L values, and let's discuss that. So remember how I gave you negative 210 and negative 196? Those are those two values right there that I just told you. The melting point and the boiling point of nitrogen. Now, we are trying to find the phase change from liquid to gas. What did we call that again? Vaporization. So, do I want LF or LV?
LB.
Because V stands for?
Vaporization.
What does the F stand for again? Fusion. This is if you were going from a solid to a liquid. You would use this column. But since we are doing vaporization, we're going to use this one. So that is our L value right there. It's pretty easy. It's just that you have to understand the idea of what's going on. So many people get lost with this because they're like, what's happening here? How do I change all these phases? We could do a problem where we go from a solid to a gas and go through all the stages. We'll have 5 of them. We'll go increased temperature, phase change. Increased temperature, phase change. Increased temperature. We'd have 5 separate Qs that we have to then sum up. And we'd have to use LF and LV actually. Okay, imagine water going from negative 20 to 200. It goes from a solid all the way to a gas. It has to melt along the way, then it has to evaporate. Okay, so we're going to use this value right now. 2.01 times 10 to the 5. Actually, let's go to a new problem because clearly we don't have the C value for nitrogen. Let's try another one. Okay, but we did all the work already, guys. We did all the work that we needed to.
Why don't you just plug it in?
But yeah, we're just plugging in. Let's do a problem where we will plug in now with something we have. So, what do I have up here? Do I have oxygen up here? No.
You did.
I have iron up top? Do I have iron down below? No.
Well, that's not fair.
What about
Exactly.
ethyl alcohol? No.
It's like metal. These are like-
Lead.
Water.
All right, lead it is, or water. I'm trying to avoid water because we always use it. It's the easier one. Let's do lead. Let's do lead. Okay. So what's the constant for lead up top we have? Was it 128? Yeah. 128 is lead C value. And lead does not matter what state it is, clearly, because it's only given one. So we're going to use lead. So here's our column right here we're going to go to. So if I give you a problem for homework tonight, I'm not going to give you the melting or the boiling point because you have it in your textbook. I'm not going to give you the latent fusion and the latent vaporization because you have it in your textbook.
Chapter 9.
Okay, chapter 9. But you do need to know the value of lead for C, which is up there already down. Okay, that was the C value for lead. So, who can come up with a problem to do here? Because I can do it easily. I want to see if you guys really know what you're doing. Come up with a problem for lead, Julian, and I'm giving you criteria. Ready? I want the lead to go from a solid to a liquid. Solid to a liquid. Give me a problem that would cause the lead to go from a solid to a liquid.
Oh, okay.
Julian,
So,
you can help if you need help.
what you can do, can't you like, your house caught on fire,
Okay?
and then your house starts with, but, I mean, that's perfect.
That's fine. Just use Celsius, don't worry.
Alright, your house starts burning at 100 degrees Celsius. So, then after,
I'm just going to put this. Okay? House burning at 100 degrees Celsius. Keep going.
okay, and then after, after
6
6 hours,
okay.
it heats up. It heats up to 2,000 degrees Celsius.
Ooh, Jordan.
You went a little too far.
800?
The boiling point is 1745. So that would bring you to a gas, wouldn't it?
Oh, you went,
I said liquid.
Oh, you said liquid, so you gotta go with motion.
So I gotta go bigger than this, right? Because that's when it'll start to turn into a liquid. But if I go past here, it'll turn into a gas.
Yes, alright, so you're 15,
15?
1500.
Well done. You see how you can make your own problem up, guys? That's all. And what's the mass? How much lead? What was the object that was lead? Give me a mass.
The object is
100 pounds.
150.
Well, we gotta do kilograms, so
50 kilograms.
100 or 50 kilograms. Good. So some mass of lead. It doesn't matter. He said 50, he said 100. I'm just picking one or the other. So we've got lead inside of a house, 50 kilograms of lead, which would be insane, by the way. 50 kilograms of lead is a very large amount of lead. At 100 degrees Celsius, going up to 1500 Celsius, we know that the mass of the lead is this number. Clearly, we're going to be melting, right? We said, because we're going from a solid to a liquid. So let's write this in parentheses. Since we're doing lead, this is a solid to a liquid. We're going to use this problem. Solid to a liquid. So when I do this problem, what's going to happen? Christian, step me through the process here.
First, you're going to take the equation for changing heat.
Okay. Give me like stages though first, then we'll put the heat below them like we did last time. Okay, so we got solid at what temperature to start?
100 degrees Celsius.
Then, when's the phase change going to be?
327.3 degrees Celsius.
PC, phase change. There's a phase change there at 327. Then it gets up to
Liquid at 1,000.
1500. But I got you. That's what's going on. We've got a solid at 100. It goes up, it heats up, it heats up, it heats up, hits the melting point, it starts to melt. A lot of energy is needed here. Then it heats up even more. The liquid keeps heating up till it gets to 1500. So how many parts? 3 parts again. That's why I'm having you guys draw these diagrams. I'm telling you, it's a whole new world. I didn't do this last year this way, and last year's class got really lost with this stuff. Okay, so I'm trying to introduce a new way, which I think will help.
When you're plugging in the delta T, it's between solid and the phase change.
Yep, and then, so here, let's list our values. M is what, everybody?
50 kilograms.
Okay.
Kilograms.
The C value of lead, what did I say?
1.28.
1.28 times 10 to the 2, so I'm just going to put 128, and this is going to be joules per kilogram Kelvin. What's my delta T in this region now?
Whatever 327 minus 100 is.
227. Again, this number minus this number. Okay, we're just subtracting, that's all we're doing.
So 27.
So I've got M, I've got C, I've got delta T. What do I do with them?
Plug them in.
Into?
The equation.
Good, or just multiply them. Very good.
Wow, I didn't see that he wrote the 27. Wow.
Okay, and my change in temperature, I'm going to put kelvins there. So I can get a Q value from those 3. That's the heat needed. That is the heat needed just to warm up the solid. Then we're going to need to figure out the heat needed to melt it. Then we'll figure out the heat needed to warm up the liquid even further. Now, what was my formula for the phase change again, everybody?
Q equals ML.
ML, just ML. This is the easy part, isn't it?
Yes.
I mean, look, Q equals ML. Mass is 50 kilograms. L is right here.
It's always given.
Why do I want L of fusion? What does fusion mean again?
Because you gotta go
Good. Solid to liquid or liquid to solid is called fusion. So we're going to use the latent heat needed for fusion. We find our number here and look at your units. Joules per kilogram. The kilogram will cancel with that kilogram, leaving us joules. Again. So 2, 4, 5, 10 to the 4.
These are going to be huge numbers.
Joules per kilogram. That's that value. So that's going to be the Q2. So let's do this. Call this Q1, call this Q2, and we're going to call this Q3. And M and C are the same. So I know M and C are the same here, so it's going to be 50 kilograms times the C of lead. But now my delta T is what? Come on, people in your head, let's go. 1,500 minus 327.
13.
It's 11.
I'm not even paying attention.
Where are you? 1173. You missed the 53.
Oh.
See what you did?
I know I can do that.
Okay. 1173. Again, what is this value? This is delta t. Just look. Say this number went from here to here. It's increasing, right? So it's a positive sign. Thus my Q will be positive because I'm adding heat. I'm adding heat. I'm not removing heat here. I did 1,500 minus 327, 1173, and that's going to be kelvins. So you need to multiply these three numbers here. I'll underline in red.
10,000,
You're going to multiply these three.
10,185.
Oops, not those three. That was stupid. Oh, man.
I'm wrong.
There's no undo feature on here. All right, let me do it in black. You're going to multiply these three numbers here to get the Q needed to warm up the solid. You're multiplying these two to get the Q needed to change
You
the
add all the Q's
phase.
together, right?
You're going to multiply these three to get the Q needed to heat up the liquid then. So what's the Q needed from beginning to end is the sum of those three.
Really?
So Q net
It's all three together.
is the sum of all your Q's, Qn, where n ranges from I equals 1 to n, meaning however many you have. If you have 1, there's just 1. If you have 2, it's Q1 and Q2. 3, Q1, Q2,
What y'all
Q3.
fools get?
Okay? All right, let's go on to the next one.
Bye, I thought you were
I don't really care about the number that much, to be honest.
telling me I punched in all
I know.
Sorry.
I'm gonna waste my time.
I'm only saying that because I'm trying to get to another tough example. All right, let's leave that up there. Let's do water this time. We're all good with water? Okay.
If you say so.
By the way, people, take a look. This says water here. I'd really rather you put H2O. Water assumes it's a liquid form, doesn't it?
Yes.
But clearly, we're talking about going from melting to boiling and stuff. So this should really say H2O or dihydrogen monoxide.
You should like break
Okay.
them and tell.
Oh,
I mean, water assumes liquid. Ice assumes solid. Steam assumes gas. So let's write H2O or dihydrogen
But
monoxide.
I just always break them.
All right. So let's say
I
now,
think I said that one time when I went to go get water.
can I get some dihydrogen monoxide?
Just to throw them out.
Nobody ever calls it that. Though. They just H2O.
They were like,
Let's say we're doing H2O from negative 30 to 120. We'll say we're doing 15 kilograms of it from
that's not enough.
negative 30 to 120.
What?
So you're adding heat.
Two-phase changes?
So what am I doing?
You're adding heat.
I'm adding heat again. I'm definitely adding heat. So we say, I'll say it.
Two-phase changes.
Two phase changes. We get to 0, we melt. We get to 100, we boil, and then we keep going. Two phase changes. So I've got the increase in temperature, phase change. Increase in temperature, phase change. Increase in temperature. How many parts?
3.
5.
Right.
The three temperatures.
Oh, yeah.
So increase temperature, change. Increase temperature, change. Increase temperature.
From
There's 5
-30
separate
to
parts.
0,
Actually, it's
from
still
0 to whatever the boiling point is, and then from boiling point to and then go to the three temperatures, and then
Negative 30 Celsius is going to be a solid until you get to 0 Celsius. Then we take 0 Celsius to 100 Celsius. Then we take 100 Celsius to 120 Celsius. Why am I stopping at these 2 points here?
go to the phase change.
Very good. This is going to be our fusion state. Okay, then we're going to be in liquid in here. Oops, QUID. Then we're going to change into a
Wait.
vaporization.
Why don't we just put vaporize?
And then we have our gas phase. Okay, so we got solid, warm it up, melt it down to water, warm up the water, boil it off into gas, let it go another 20 degrees Celsius. So we're going to have 5 parts of this problem now. We're going to have Q1, Q2, Q3, Q4, Q5. Whenever you see the word vaporization or fusion here, you know it's going to be Q equals ML. The other one's going to be Q equals MC delta T. So again, this is going to be MC delta T in this part. For this part for fusion, it's just going to be ML. For this part from 0 to 100, it's going to be MC delta T.
Sounds like a game.
At vaporization, it's going to be ML. And then again increasing, MC delta T. Okay? The part here that we have to consider is that the C value for water is different depending on my phase. And I talked about that a minute ago. Okay? Take another minute to write that down and then I'll show you the table. So this I'm going to call L.
2, 3.
Okay, C1, C2, C3. This is going to call it LF. This is LV. Make sure your subscripts are recorded. So this LF here corresponds to fusion. LV, vaporization. All right, so let's look at our table. We've got our fusion for water here. We've got our vaporization for water here. Which is bigger?
The after one,
Vaporization.
Vaporization is bigger. People, guys, look at the exponent, please. You all see 3.33. You want to say this is bigger. 10 to the 5th, 10 to the 6th. This is an order of magnitude larger. And yesterday, by yesterday I mean Tuesday, of course, on Tuesday, we talked about the fact that it's more difficult to boil than it is to freeze. Remember that? We said it takes more energy for vaporization. Here's your proof right here. The latent heat of vaporization, these numbers are much larger than the latent heat of fusion. Okay? All right, so those are my L values. So now I need C1, C2, C3.
Where's the other graph?
C1. What state am I in again there?
solid.
Solid. So if I go to my other graph here and take a look at it and move up, I find water as a solid. What do we call that?
2.1.
2.09 times 10 to the third. Nice. So we go back to our chart.
Why didn't you just call me
2.09, I have no room, times 10 to the third. I'm dropping my units for a second here because I'm running out of room. That's the only reason. I know. After ice, it becomes
4.186 times 10 to the third.
good. So after ice, it becomes water. Thus 4186, 10 to the third. Finally, it becomes steam or gas. 2.01. And I don't know why it goes up and then comes back down. I got to figure that out. I haven't studied it enough.
What are you talking about?
Look at the specific heat capacity. It goes up and then it drops back down. Steam and solid are pretty much identical, right? But look at the liquid. Very different.
That's what you get.
Almost double. Actually, double pretty much. Yeah. 0.9 double would be 1.8, right? So this value is almost exactly double the C value of solid. I don't know why. I think it has to do with the hydrogen bond being different than most bonds. I'm not sure. Yeah, the answer is Jenkins 1. She would know that.
She would.
She should. I mean, they talk about this in chemistry. All right, so what's the mass of this problem, guys? What was the mass we were looking at here? How many kilograms?
15.
15. So for all these problems, what can I really factor out?
15.
So here's what I'm going to do. That's what I'm going to do here. And I think you guys will like this. Make it a little easier on you.
Really?
Oh yeah, you know what's right.
Q net equals the sum of all the Q's. So Q net is really M1 or M C1 delta T plus M LF plus M C2 delta T plus M LV plus M C3 delta T.
Can't you factor out M too?
Okay? So I factor out my M, absolutely. But my delta T's are different, aren't they? So I should really give them subscripts also. But the M is consistent. The mass is not changing. We're imagining it's in a container that has a lid. Because if it didn't have a lid, the gas molecules would escape, right? And then the mass can actually change. So here, let's factor out an M. Now, do you see why this kind of a problem would be a great example that says find the mass, because so many students, you know what they will do? They'll try and solve for the mass here. Good luck.
Good luck with
I mean, if you knew the Q, and you knew delta T's and all your C's and stuff, try finding the mass here without factoring on M. You have to do it on the calculator, obviously. But if you factor on M now, if you want to solve for M, Q net divided by whatever this number turns out to be. See what I'm saying? So you can easily solve for M in these problems. You can easily find, and I'm telling you now, you might have to solve for M. Okay, it'll say how much mass of water is needed if this much Q is given, and you know these factors. They tell you everything else.
Would that be a mistake on the AP physics test?
To not solve for M, or? Definitely a problem on the AP physics test for sure, this kind of problem. The common mistakes on that would probably be switching up these two, or using the same C for all three, or not factoring on M. Yeah, I can see that, but you're given a calculator, so you technically could solve for M here, even if you don't factor it out, if you just graph the function in front of the roots, you know? But I could see that, yeah. All right, so we know all these values, right? Elizabeth, can you go through them for me? No? I'm going to drop units because everything's in standard units at this point. Who wants to help me with all these numbers? Just run them across for me. You have it on your paper.
2.09 times 10 to the third.
All right, so I'm going to write 2090. Everybody see that for C1?
Yeah.
Instead of 2.09 times 10 to the third, I'm going to simply move the decimal 3 spots. Next, what was my delta T, Elizabeth? From the original to 0 Celsius.
30.
30, very good. Let's go over that real quick, just so we're all clear. We started at negative 30. We went to the fusion point. How many degrees went by? 30. How many degrees go by here?
100.
How many degrees go by here? So that's delta 1, delta 2, delta 3. Continue, Elizabeth. What was LF? Next is LF. You didn't write it down? All right, I got it. It's all right. Look up here. LF was right here.
3.3.
So tell me as a number, as a non-scientific.
3.30.
What does the 5 mean to do? Move it how many spots?
5.
So 2 spots will get us to here and 3 more. So 333,000.
Oh, there you go.
That's LF. So we've done this part, and we've done this part so far. What was my C2?
4.186 times 10 to the
I'll
third.
take you to the campus.
Times 100. Tell me, where does the 100 come from?
The
Julian. Between?
The liquid and the
Let's say the melting point and the...
avoiding.
Very good. I know what you meant, but use the words. So we've done these 3 now. Elizabeth, latent heat of vaporization. Did you write that one down or no?
That's 30.
All right, we got
2.36.
times 10 to the 6. That's 2.26 times 10 to the 6 there. That's what that is as a number. Finally, last one.
2.01 times 10 to the third.
So 2010. Okay. Oh wait, I didn't do this one, right? I should fix that. What was this? 4186 times 10 to the third?
Yeah.
So that should just be 4186, no decimal there. Make sure you correct that. Okay, it was 4.186 times 10 to the third. And this is times the delta, which is?
Oh shoot, 20.
Close your big parentheses. Again, all we've done is plugged in for all of those, okay? That's it. I did, look at the very beginning.
Oh, wow.
Here's the opening really. I can use a bracket if it helps. And there's the close. Because 15 needs to be multiplied by the sum of all these numbers. So if we were solving for the mass here, we would get a numerical value for this, and then just divide it into Q to get the mass. Again, if you're given Q, and you're not given the mass, you do all this work, get a number, and then just divide it into Q to get the mass. But we're looking for Q. Okay, we're looking for Q. Yeah.
My calculator's still dead, so
Anybody actually get a number from this? The reason I want an answer here is because I'm going to convert to kilojoules, just to make sure we're clear on how to do that. Because it's going to be a huge number. Some number with joules, and then we're going to convert that to a number
Maybe about 2 million.
in kilojoules. Or you know what, actually? We could probably do megajoules, and I'll explain that one.
About 3 million.
1,000 kilojoules.
Maybe a million, maybe a million,
1,000 kilojoules is a megajoule.
1,000 kilojoules.
2 million to 2 million.
I thought the answer was.
Anybody got the-
Kilobyte, megabyte, gigabyte, terabyte, all thousands.
My calculator's
Yeah, Christian's doing it, I'm looking at him.
Mine, man.
You want me to read it? Where are you at?
No, I'm at 2 million.
2,260,000
Oh, no, never mind, it's gonna be like 6 million.
plus the product of 2010 and 20. Close. You do the 15 in the front, or you gotta multiply stuff? What do we got? It's probably gonna be in scientific notation.
1.63 10 times 10 to the 12.
Times 10 to the 12. Okay. So let's discuss this now. This is gonna be a huge number. 10 to the third is kilo. 10 to the 6 is mega. 10 to the 9th is gigabyte. Giga. 10 to the 12 is tera. So this would be 1.63, not kilojoules, but terajoules. Again, I'm not worried about that. TJ, terajoules, where's Terrence? Terajoules though, terajoules, okay? So tera means 10 to the 12. Don't worry about that as much, but I want you to be able to see that. Okay? So here's your homework for tonight. You're gonna do one problem. You're gonna do a problem that has this exact same setup. Okay? So here's your problem. Now, I'm telling you now, guys, you're gonna need this table. What I'll do is I'll post these on Facebook and on Edline, so you don't need to bring home your book if you leave it here. Okay? So you have these tables. But I'm not telling you the numbers. You look it up. You figure it out.
Oh, true.
Oh, geez, you want us to write it?
Aluminum,
Oh.
20 kilograms of it from
Are you recording? Or you just go to...
Okay? That's your problem for tonight. You need to figure out, listen carefully please, we're going to write down steps. Step 1, identify the phases that's happening. Identify the processes that's going on. So you're going from where to where to where to where and stuff. Next, set up your Q equations. Identify your values for like LV, LF, the C value. There's no C value that's different for aluminum, it's just one C value. Okay? Then figure out the actual value for Q. So find the Q value to do this. All right? Again, tables will be on Edline. Take a look there tonight.
You didn't give us some back. Oh, no,
Oh, what?
Yeah, you didn't get it.
Doing it.